Okay, so in appointment scheduling, we once again have Alice and Bob, who are far apart. Alice is given some classical input x. Bob has some classical input y. And in appointment scheduling, what they wish to do is to find some index I where both xi and yi is equal to 1. Okay, so this is a common date of availability. So it's known that if Alice and Bob only have access to classical resources, so classical communication, for L bits inputs, they essentially need to exchange their all input. Okay, so they need order L communication. But if they have access to quantum resources, then this is essentially some distributed version of Grover search. Okay, so they can get quadratic speed up here. Okay, so in particular, it's not how to do to solve this problem with square root L messages, which are each constant size messages. Okay, and this is also known to be essentially optimal, both in terms of total communication square root L, and also in terms of the interaction required to achieve such a quantum speed up. Okay. So let me describe an almost optimal protocol to do so. So essentially, they wish to perform some distributed search. So Alice can initialize Grover, like perform Grover initialization. So uniform superposition over a log L size register. And then, well, before she performed Grover inversion about the mean, she wished to interact with Bob in order to perform a Grover oracle call. Okay, so in order to do so, she'll first perform some quantum unitary on a register based on her classical input x. Then she transmits the register from to Bob. Then Bob on his side will also perform some unitary based on his classical input y. Then transmit back the register to Alice. And Alice will perform some further unitary based on her classical input. And then at this point, they have succeeded to essentially distributively perform the Grover oracle call. Okay, so then she can perform the inversion about the mean, and they repeat this for square root L times. Okay. And then at the end, they hopefully measure and output some intersecting index I. Okay. So this is the type of interactive protocol we're interested in communication complexity. So more generally, in this talk, we'll be interested in such a generalization of these interactive protocols. So we'll allow for arbitrary quantum inputs. Okay, so for a given protocol pi, the input will be some tripartite quantum state, psi n, over register A, B, and C. And then once the protocol starts, Alice and Bob will interact and apply a sequence of unitary in order to prepare some output state here. So protocol runs as follows. So Alice starts with register A and C. She applies some first unitary U1 in order to prepare a message C to transmit to Bob, register C. And, well, once again, ideally, they wish to transmit this over some perfect communication channel. So an identity channel going from Alice to Bob here. Then upon reception of register C, Bob will apply some unitary U2 on register B and C to prepare a new communication register C to transmit back to Alice. Okay, so register C here, which is transmitted over an ideal channel back to Alice. We can then apply some further unitary U3, prepare a new communication register to send to Bob, and back and forth, okay, in such a way. And then at the end, after the nth message received by Alice, she applies one last unitary, prepares like the output AC register, and in this way, they prepare the output state psi out. So a given protocol is defined by this sequence of unitary, U1 up to UN plus 1. And one thing to notice is that, okay, even though there's a large number of communication in the protocol, each of these messages are created online. Okay, so messages cannot be transmitted in block, as in one-way communication case. Okay, each of these messages are created online in an online manner, one after the other. So one reason to study this topic is that we can get some provable quantum advantage. Okay, so quantum communication is a powerful resource. So as we saw for appointment scheduling, we can get this quadratic advantage for that problem. And in fact, there's even some specially crafted problem for which we can get exponential quantum advantage. Interaction is also a very powerful resource. So for appointment scheduling, I mentioned that, in fact, in order to get any quantum advantage, Alice and Bob need to interact a lot. And for interaction, too, there exists some specially crafted problem for which we can get exponential saving by adding even a single more round of interaction. So now getting to the topic we're interested in today, that of noisy interactive quantum communication. The setting is as follows. So we wish to simulate such highly interactive quantum protocol as we just described. But Alice and Bob only have access to a noisy quantum channel M available in both directions. Okay. So how can they succeed in implementing such highly interactive quantum protocol over noisy channel? That's what we will study today. Okay, so of course, we'll allow them to perform some encoding procedure. And then what they wish to perform is essentially simulate this interactive procedure by generating the correct output state up to some small distance delta. Okay, so similar to the one-way case, then we define the rate as the ratio between the number of ideal channel we have to use, n in the ideal case, versus the number of noisy channel required for the simulation, so n over c. Okay. And then the two-way capacity for this noisy channel m is just the best asymptotic rate that we can achieve in order to perform such a simulation over the worst case protocol here. Okay. And such that the final distance in the end goes to 0, too. Any question about the setting before we move on? So in the remainder of the talk, I'll start by discussing some of the major difficulty that we face in order to perform such interactive coding. Then mention previous work tackling these problems. And finally, I'll get to our result in this setting. Okay. Now on to difficulties. So what are the major obstacles that we face for simulation of such highly interactive protocol over noisy channel? Okay. So the first one is that standard error correcting codes are not applicable in this setting. Okay, so, and this is a problem that we face in both the classical and the quantum setting. Okay, so error correcting codes are well suited for one-way communication when we can encode by block. But here, if we try to do so, well, one approach to do this would be to try to run the original protocol as is, but each time we're trying to communicate some register over an ideal channel, we would try to simulate this ideal channel by using some error correcting code. Okay? So instead of directly transmitting the communication register over the noisy channel, we first encode it, then transmit over some copies of the channel, decode, and then hopefully we get the good message, and then we can just run the protocol as is, except we encode each communication. Okay, so, but then this does not work well. So, and the reason is that, well, even if there's a single such transmission which is corrupted, then this derailed all the rest of the protocol. So if there's an error which happened at the beginning, then all the rest of the computation is useless. Okay, so one way to think of this is, well, just think that you're having a conversation with a friend. Okay, so he asks you, what did you do last night? And you reply, well, I went to the movies. But then what he hears is, I went to the groceries. Okay, so whatever you'll be discussing after might be totally useless because you're continuing the conversation assuming that he knows you went to the movies. But then he's continuing the conversation thinking that you went to the groceries. Okay, so whatever else you're discussing after is not based on good assumption. Okay, so such use of error correcting code does not work well because, well, you will want to make sure that not a single message encoded in this way is corrupted. Okay? So as the length of the protocol increases, you have a lot of small messages, but then you need to encode them in larger and larger error correcting code to make sure that not a single one of these is corrupted. Okay? So what you get, even for random ID errors, is that, well, the block size for each error correcting code has to increase with the length of the protocol, and the communication rate goes to 0 in the end. Okay. In the case of adversarial error, it's even worse. Okay, so the adversary could just choose to take all of his error budget and apply it to the very first message. Okay? So in this way, whoops, sorry. He only has to corrupt a single block, and no matter what communication rate you're using, the error rate that you can tolerate decreases as the number of rounds increases. Okay, so you can tolerate adversarial error rate at a rate of at worst 1 over a number of rounds. Okay. So what we do need is some coding strategy that doesn't work message by message, but somehow act a bit more globally on multiple messages at a time. Okay. And another thing to notice is that, well, in the sense we just described, interaction makes problem harder, but it also allows for new opportunities. Okay? So in particular, instead of requiring error correction right away, we can instead aim for error detection. So if one of the party realizes that the conversation is not going well, like he detects some error, then he can let the other party know, because now they can interact at least. And then, well, they can try to recover from previous error and restart from a point of common agreement thereafter. Okay, so interaction also provides us with new opportunities. So another major difficulty, which is uniquely quantum, is due to the no-cloning theorem. Okay, so notice here that as the protocol goes on, like the joint quantum state evolves with the protocol. Okay, so as we apply the sequence of unitary in the protocol, the joint state is changing, and we cannot make copies of previous state in the protocol. Okay, so once we arrive at some point in the protocol, we don't have any copies left of previous point in the protocol. Okay. And in particular, it's not possible to jump back to an earlier point in the protocol, and any logical quantum data linked to the environment cannot be recovered. So let's move on to prior work on this interactive coding topic. So this topic was introduced in the classical setting by Schulman in the 90s. And Schulman proved that despite these obstacles, it's possible to achieve communication rate greater than 0. Okay. So in particular, Schulman's work used so-called tree codes, which are online self-healing codes that have very low communication rates. So in particular, the rate he achieved were still much lower than 1, even as the error rate goes to 0, where in the regime where you would expect that communication rate should go to 1. Okay? And well, ever since, it's been a very active field in classical literature, with lots of work, and in particular, two work are most relevant for the topic we're discussing today, those of Colin Raz and of Haeupler. Okay, so these two work establish the two-way interactive capacity to leading order. Okay, so they prove that as the error rate of the noisy channel goes to 0, it's possible to achieve communication rate which go to 1, even in the interactive setting. Okay, so Haeupler showed that in the case where we assume large communication alphabet, even if we have either adversarial or random noise, the communication rate we can achieve for error rate epsilon is at least 1 minus something growing as square root epsilon. Okay. But then in a small alphabet case, so for example for binary communication channel, he conjectured that the rate which is possible to achieve is strictly smaller, like growing like this. Okay. But for random noise, even for small alphabet, we can still achieve this 1 minus square root epsilon rate. Okay. Now in the quantum setting, to the best of my knowledge, there is only one prior work studying this topic. So some joint work with Gilles Brassard, Ashwin-Nayak, Alain Tapp, and Falconger, in which we proved that in the quantum setting too, despite these obstacles, it's possible to obtain communication rate strictly larger than 0. Okay. And in that work too, we're using 3 codes. So particularly, we were able to sustain very high error rate, but the communication rate that we obtained were quite low. So they're still bounded away from 1, even as the error rate goes to 0. Okay. So now on to our work. The main result that we prove is that even over fully adversarial binary quantum channel, which corrupts at most some small but constant epsilon fraction of the channel uses, it's possible to achieve some communication rate going to 1 as the error parameter goes to 0. Okay? So we achieve this 1 minus order square root epsilon rate with very high fidelity in the distance at the end. Okay. So a few remarks, I guess, at this point. So the first one is that, well, we're able to achieve this in so-called plain quantum models, so where we do not assume any pre-share entanglement, and we communicate directly over quantum channel, so we don't assume any secret key or pre-share entanglement. And in particular, for the binary case, this outperforms the conjecture best optimal classical rate. Okay? And intuitively, why can we do this? Well, it's using the fact that since we have a bounded error quantum channel, we can use it to distribute some secret key at the outset. Okay. So yes, indeed. So this is the first result achieving like two-way interactive channel capacity up to leading order. So as I mentioned, the communication rate goes to 1 as the error rate goes to 0. And it's also the first computationally efficient interactive coding scheme. So for the rest of the talk, try to discuss a bit about the framework we developed. Then spend some time to discuss one of the major obstacles that we face, what we call out-of-sync teleportation. Finally, I'll do some crude analysis of how we obtain this rate of communication of 1 minus square root epsilon. Okay. So in order to develop a framework, we studied four simpler case. Yeah. So our ultimate goal, recall, is to show that we can obtain such high communication rate for binary quantum channels. But first, we considered the simpler case where Alice and Bob start with perfect pre-share entanglement, and they communicate over a noisily classical channel. And we also make the large alphabet assumption, which simplifies some things. Okay, then we extend this framework for the plain quantum model, okay, where there is no pre-share entanglement and communication is done over a noisy quantum channel. Okay. Then we first do so in the large alphabet case, and then we move on to, for both settings, to small alphabet case. Okay. And in particular, like the way we set up large alphabet case allows us to use some of the mechanism developed for small alphabet in the classical setting due to Haeupler. Okay. So the Scarfeld initial setup allows us to get mostly seamless transition between all of these settings. And today, apart from the very last slide, where I'll discuss a bit about plain quantum communication, for the rest of the talk, you can assume that we're establishing the framework in the perfect pre-share entanglement setting with noisy classical communication. Okay, so that's what I'll be focusing on for most of the rest of the talk. So perfect pre-share entanglement, large alphabet communication, and noisy classical communication. Okay, so right here. So let me first review the most relevant work in the purely classical setting that we build on. So the way that Haeupler makes a conversation robust to noise is as follows. So we can think of both parties communicating over some low noise channel, and then they're having their conversation essentially as is, so without any encoding. So they run the original conversation as if there was no noise, but then once in a while they will exchange some summary of the conversation so far. Okay, so let's say you have a conversation that you know beforehand will be of length n, okay, some parameter n. Then you'll divide this whole conversation in blocks of length r, okay, for some small length r. So there will be n over r blocks of size r for the whole conversation. Okay. So you just run all of these blocks as is, but then in between you will exchange summaries of the conversation so far. Okay, so it might be hash of the bit you have exchanged so far in the classical setting, so on. So you just run this part as is, of the protocol, exchange summary. Then if the summary are consistent, what you'll do is you just, well, continue. Okay, so everything seems to be looking good. You can continue running the protocol as is. But then if you realize that your summary are not consistent, well, this means that you have detected some error. Okay, so what you'll want to do is, well, you just want to go back to an error point and resume from that point. So hopefully at this point everything went well, and you just rerun the last part of the protocol. Okay. So as we said earlier, so this we use the fact that we have an interactive protocol here to our advantage too. So we don't necessarily have to encode the whole protocol. We can just run it as is and use error detection once in a while. And if we do detect an error, then we just go back to an error point and rerun the protocol. Okay. Now let me also recall about the previous work in the quantum setting, if we will done. So first of all, well, let me state the difference between this previous work by Brassard et al. So I guess here our focus is on the low noise regime, and we're able to show that as the error rate goes to 0, the capacity goes to 1 for such interactive communication. Whereas Brassard et al. Showed that, well, it's possible to generate very high adversarial error rate, but then even as the error goes to 0, the communication stays bounded from 1. And in that work, they use these 3 codes, and they also expanded all messages in order to convey more information. Okay, so it's not possible somehow to combine this with Haeupler's classical framework and hope to obtain directly high communication rate. Okay, so the rate possible to attain with this setting is bounded away from 1. Okay, but still there are some of the main idea that were developed in that work that we adapt here. Okay, so one is the idea of reversing rather than backtracking to an earlier point. Okay, so this requires extra communication. Let me explain a bit more here what we mean. So for all these classical work, we call that whenever we detected some error, what we wanted to do was to directly jump back to an earlier point in the protocol. Okay, so let's say Alice and Bob run the protocol, then they run their check, like they exchange summaries, and they detect some error. Okay, what they wanted to do was to jump back directly to some earlier point in the protocol. Okay, but then in quantum setting, due to no cloning, well, there's no copy of the state at this earlier point in the protocol which exists. Okay, so instead, Alice and Bob have to find some other way to get back to this earlier point. Okay, so that's what we call reversing here. So instead, what they'll want to do is to go back one step at a time by using more communication, and they'll want to go back to this earlier point one step at a time. So Alice will need to communicate to Bob so that Bob can reverse his unitary and then Bob will communicate back to Alice so that she can reverse her previous unitary, who communicates back to Bob to reverse another unitary, and finally, Bob can communicate again back to Alice, who can reverse the first unitary, and then they can resume from this point. Okay, so instead of jumping back to an earlier point, they really had to actively reverse the protocol, and then they can resume. Okay. So another idea that we adapt, at least for the classical setting here, is the idea of using teleportation to protect the quantum data. Okay. So since we're communicating over noisy channel, and we don't want to lose any quantum data because no copy of it exists, how we deal with this is by using teleportation. Okay, so one of the main features that we're using here of teleportation is that, well, it's actually splitting the logical quantum data into two parts. Okay, so some quantum share, okay, which is protected. So this quantum share uses the perfect pre-share entanglement. Okay, so it's somehow protected. And then there's some classical share, which is unprotected, okay, which will be communicated over the noisy classical channel that, well, Eve has access to. He can see, he can corrupt this classical data, but at least quantum share is somehow protected. Okay. So now on to our framework. Yes, one of the main driving idea behind the framework is that, well, we wish to keep both parties informed about the global quantum state at each point in the protocol. Okay, so we want them both to know everything which has happened over the quantum register at each point. So in order to do this, well, we need to introduce sufficient but concise data structure. Okay, and this data structure will keep track of many things. So if we have here on the right the original protocol to be run over the ideal perfect communication channel, so they'll want to know at which point they are in the simulation. Okay, so which unitary they're acting now. So what the type of action they need to take next. What's the history leading to the above? And also they want to know, since they're running this with teleportation, they'll want to keep track of the teleportation history. So teleportation measurement outcome, decoding operation, maybe some history of the recovery operation if they've had some error and try to recover from them, and so on. Okay, so like they really want to have some classical description that they both hopefully agree on of what's happened up to this point in the simulation. Okay, so how they'll do this is they'll have some data structure. Let's call this global data structure DA for Alice and DB for Bob. And well, on Alice's side, DA will contain all the operations which have happened on Alice's side. Okay, and in DB, it will contain all the operations which have happened on Bob's side, such that if we take DA and DB together, we have the whole information about what has happened during the simulation. Okay. But then, well, Alice knows DA, but she doesn't know DB, and vice versa. So they will want to keep some estimate about what has happened on the other side. Okay, so that's what we'll call the estimate DB tilde that Alice has about what has happened on Bob's side, and vice versa. So yeah, let me skip this one just in the interest of time. Okay, so let's now see in a bit more detail what's happening in each of these blocks of size R. Okay, so recall that we split the original conversation into blocks of size R. So let's zoom in into how we simulate each of these blocks. Okay. So the framework we develop is as follows. So we consider here two cases. So on the left here, we have the case where Alice and Bob both want to move the simulation forward. Okay. So they want to essentially continue running the original protocol. And then on the right here, we have a case where they're trying to reverse the original protocol. Okay, so they're running it backward in order to try to recover from some previous error. Okay. So when they're running forward, they're applying sequentially the unitary from the original protocol. And then whenever they wish to communicate the communication register, then they're trying to teleport it. Okay. So for a block of size R, we have Alice starting here. Then she transmits by teleportation to Bob. He's running his unitary, transmitting the communication register back to Alice, and so on. And then Bob applied the last unitary. He teleports back to Alice. And then at the end, she just applies some identity operation. Okay, so she's getting ready for the next round, essentially, by applying this identity here. But then, if they're trying to recover from some previous error, well, we want the operation happening here to essentially be the reverse of what's happening here. Okay, so instead, when they're trying to reverse here, Alice will start by just doing the identity at the beginning. Then she teleports to Bob, who then apply the inverse of this last operation here at the bottom. He teleports back to Alice, who then try to apply the inverse of this operation here, and so forth, until the very end where Alice finishes by applying the inverse of the very first one when she is running the protocol forward. Okay, so. But then for each of these lines, for the teleportation, like we have like these three things happening. So there's these two circles and this square thing. Okay, so these two circles here correspond to teleportation. Okay, so for communication from left to right, so from Alice to Bob, first one will correspond to teleportation measurement. Okay, then Alice will try to communicate this measurement outcome to Bob, but over the noisy channel. Okay, so it's possible that the decoding operation for teleportation that Bob performs is not the good one. So once in a while, when they're reversing these protocol, they will have to perform some poly correction to account for this bad teleportation decoding. Okay, so that's what these square things are for, in order to account for some remaining poly errors. So so for each of these blocks of size R, like we denote it, like inside the global representation here at the beginning by this, what's inside this bracket here. Okay, so we have a direct mapping from what's happening in each of these blocks to a first representation we call just one here. So this directly corresponds to the sequence of unitary operation, these three potential poly operator there. And then, well, in order to assess more precisely what's happened so far, so this is what this JS representation is trying to accomplish here. So we cleaned up this first representation, and then we can see what Alice and Bob have been able to accomplish so far. Okay, so if we start from the input state, what Alice and Bob will need to do is essentially apply the sequence of unitary of the original protocol in order. Okay, so here they've succeeded to do this up to this UGR unitary there. So this is the good part of the simulation. So what they have accomplished so far, which is good. But then there might also remain some error due to error in the communication that happened previously. Okay, so these sharp things here are things that they want to reverse. Okay, so these are the error remaining before they can resume the simulation. So essentially, they want to get rid of all of these at the end and then increase the sequence of good unitary up to UN, the last unitary in the protocol. So then there's a lot of synchronization that need to be done between Alice and Bob. Let me skip the detail of this and discuss a bit one of the major obstacles that we face while trying to do this. So, which we call out-of-sync teleportation. Recall that in each block, Alice and Bob engage in one out of three possible actions. Okay, so either they are trying to move the simulation forward, okay, so apply unitary of the original protocol by forward, or they might also try to reverse the protocol, so apply unitary of the original protocol, but in backward manner to try to recover from previous error. But then, if they realize that they don't agree on their history so far, they might also try to exchange this classical history of the protocol before they resume the simulation, or before they try to reverse. Okay? But then, when they exchange their classical summary, if there's error over this summary, it might be that they don't even agree on what action to take next. Okay? So, for example, here, Alice might try to teleport to Bob, but Bob here is waiting for classical history of the protocol. Okay? So he's just doing nothing. So in such a case, well, we have one party who's trying to attempt to teleport and even receive teleportation from the other, but the other is not like making his part of the teleportation. Okay? So it looks like this. So we have Alice who's running inertia of the protocol, so applying unitaries, trying to teleport to Bob. Bob's leaving his end of the EPR pair there, and then, well, Alice is expecting teleportation from Bob, running the next unitary, and so on. Okay, so effectively, Alice is sending to Bob like important quantum data. Okay, so it's important that, well, in the meantime, Bob does not screw up this share of the entanglement there. So yes, what we're hoping here is that, well, at least it's possible to recover from such type of error. Okay. So in order to do so, well, what we do is that we put a lot of structure on how we use the EPR pair for teleportation protocols. So let me describe this a bit. So at the outset of the protocol, Alice and Bob pre-share a lot of EPR pairs which are dedicated to teleportation. Okay? And we split these in sequential blocks of our EPR pair for teleportation for R times. And then if all goes well, Alice and Bob will try to teleport at the same time. Okay, so in each of these blocks, Alice and Bob were trying to teleport together. All goes well, so they've used the same number of EPR pair. But then the problem we just described is what happens if, well, Alice is trying to teleport in one round to Bob, but Bob is trying to accomplish something else. Okay? So how can we recover from this? The way we do is that, well, first make sure that they have sufficient classical data to be able to recover from this. Okay? And once they do have gathered enough classical data, then some are able to complete the teleportation, okay, and retransmit back all the quantum logical data to each other. Okay, so for example, as we described earlier, where Alice was trying to teleport here, Bob did nothing. Well, once they do agree that this is what has happened, then Bob is able to complete this teleportation in this way. So he just takes the quantum data hanging in this EPR pair and feeds it back to the other end of the teleportation and transmit this back to Alice. And this allows them to recover the important quantum data up to Pauli errors. So let me skip the analysis at this point. So this is what I wanted to say about the part for communicating with perfect pre-share entanglement but noisy classical communication. Now, how do we extend this to the setting where, well, Alice and Bob don't have any pre-share entanglement and they're communicating directly over noisy quantum channels? Okay, so how can we extend our framework to this setting? So the framework does build on the one we just developed for teleportation, but then we cannot use teleportation anymore. Okay, so teleportation without pre-share entanglement has too high an overhead. Okay, so instead, procedure that we use is the quantum random cipher that they developed in 2000. Okay, so some property of this subroutine is that, well, as long as we start with a small amount of entanglement, okay, we're able to recycle it. Okay, so we developed some procedure in order to recycle it by using quantum hashing LBADSW. Okay, so this allows us to either make sure that there's no error, so that's a quantum analog of this exchanging summary. So we can use that to detect error, but an important feature is that, well, if there's no error, then we're able to recycle previous entanglement. Okay. But then we don't have to be careful only with out-of-sync quantum random cipher anymore, but also about out-of-sync quantum matching procedure, out-of-sync recycling, and so on. So I guess there's many more difficulty coming up in that setting, but still, I guess everything was well in the end. And I guess I'll stop at this point. Thank you very much.